small mechanisms for long reacting. And don't know how to do any math when you all of stuff.
Well, trivia time. Who has who has two thumbs and doesn't care about biochemistry? This dude. All right. So we were working on this problem and we were about to finish it. So we have to figure out parts C and D. Okay. So we did A, did B. So then part C says what current flows through each branch between points A and B. Okay, well, if we remember, we can use this here. Remember, because we combine the resistors in each branch.
I'm not touching. I don't want that. Just that big one.
Now, we found the delta V across that 36 ohm resistor right here, which is the combined resistors of that branch. So now that means each one of these is going to have the same delta V. Okay, so since we know that, how do we find the current in each branch? Sonia, not you. How do I find the current in each branch? Mm-hmm. And so let's look at I1. So if I1 is here, it's going to be delta V divided by 60. So then our delta V which will give us 0.678 amps. I2 Okay. Now there is a way you can check your answer. How do you do that? There you go. So you can say I equals I1 plus I2. So that's 0.678, 0.452. And what should you get for this? Is that what I should get? Is that actually what I get? Okay, so that is what I get. How do I know if that's what I'm supposed to, if that's what it's supposed to be? Right, that's what the original current calculated was. So these two currents work. Okay. So now the new part of this, determine the power dissipated in the 40 ohm resistor. So right there. So we're gonna go with so part D. So essentially we're going across the top of that loop, and we're gonna have we have those two resistors. What's the equation for power in a circuit? No, no, no. What did we say? What did we say the equation for power was? What? Okay, or what? Because I have a resistor and I have a current.
Sorry,
What does I delta V become? Nope. Nope. Yeah. So well, yeah, that's the easy part of the equation. I delta V becomes what? Nope. In this case, we have to figure out the power in the 40 ohm resistor. We only have a current and we have a resistance. If I only have current and resistance, so remember there were two different forms of power based off the numbers we have. Look back at notes that you should have taken a couple days ago. Yeah, these are new, but we've already. Uh-huh. Mm-hmm. In terms of current and resistance.
Oh,
Nope. Leave the electromotive force out of it. The electromotive force didn't do anything to y'all. Leave it out of it. There you go. There you go. So this is going to be I1 squared R40. So that's going to be 0.678 squared, and then the 40 ohms. And that is going to give you 18.4. And the unit? Yep, the old lady. What? No. But you need to get the actual SI unit. So yeah, that's what it is, but you need to know that that is watts. Most of these units are after people's names. Did we do Faraday's yet? Yeah, that's another person's name. Oh yeah, farads. Yeah, capacitors, farads.
like for this says, it's like 5 and 7 or 5 and 7.
Well, I mean, this exam is going to be circuit heavy, so yeah. But remember that you have those first 5 questions that are conceptual, so those can be, as I read through the textbook and I see a question that makes me giggle, that can go on the exam. I love going through and going, they're not gonna get that one. So,
Sorry.
it could be, yeah. But keep in mind, you like in-class examples
Yeah.
are also fair. So we're not gonna do anything that's super duper difficult because it'll take too long to work through. But it's gonna be basic circuits and it'll tell you use Kirchhoff's rules, use combination method. It's
What do we do? That be something
Mhm.
like that?
and of course that one would be the combination method where you're creating REQs and then splitting them back apart. Okay. RC circuits. These are, I mean, they're exactly what they sound like. They're called RC circuits because they have combinations of resistors and capacitors. Kind of like RLC circuits, which are combinations of resistors, inductors, and capacitors. So you notice that, okay, so what's this new little symbol that's in the circuit there? What is that? What is that new circuit unit? What is that? It's a what? Yeah, it's a switch. You need switches now because initially there's no current running through the system. You close the switch and then the capacitor starts to charge. And you're going to reach a maximum charge of the capacitor. And so you notice your top graph there is the charging of your capacitor. Your bottom graph is how the current falls off as your capacitor charges. And then you have a charging equation here. So the charge at any time t is going to be the Q max of the capacitor, 1 minus your exponential, negative T over RC. So RC is your resistance, C is your capacitance, and then so the textbook actually calls that RC, yeah. A what? So the load is anything outside the battery. So yeah, that's a load resistor and a load capacitor. Yep. So your load circuit, usually your load circuit is what connects to the power source, and then energy will run through there to the rest of the circuit. But yeah, everything outside the EMF is your load. So your textbook calls this RC. I don't like that they keep using, so now they're using the Greek letter tau for multiple things. For the thing I don't want to mention, because we'll have to talk about it again in magnetics, and we have too many perverts in this room to bring that word up. No, not that equation. Good guess though. Yes. Yeah, no, actually, no. We are not. We're not expanding on that. So
That's how I remember what those.
y'all need to get off TikTok. You need to stop reading smut. You need to. Okay, okay. But, not too long ago, I saw a young lady on TikTok talking about pickled foods. Yeah, no, she goes, well, I've seen pickled peppers and well, she had all kind like pickled peppers, pickled asparagus. She went through this list. She goes, but what upsets me is no one's ever pickled a cucumber. TikTok is trash. Most of the people on TikTok are trash. It's a waste of your time. So now, the what? The only TikToks, well, I would say most of the TikToks worthwhile have to do with animals. I don't have Facebook, so I don't know. Yeah, but it's animals like Tatum. Tatum's worth your time. Chili the pug, worth your time. Okay. The ones I really don't understand are the people who film themselves crying and then put it on the internet. Like, do you expect me not to make fun of you? Like, I'm already sad. How could you make fun of me? Because you put it out for the world to see. That's your fault. So the question is, how do we actually get to this charge? How do we actually get to this charging equation? No, we're not. You're not going to do derivations on the exam. It can take too long. Because I know that that's something you're all still learning how to do. So if like that for some people it would take like the whole time, but not necessarily. But it just when it's something new that we're trying to teach you, that could take too long for the exam, but they will continue in the homeworks. Like on this recent homework you had, the derivation was like 3 steps if you knew the right substitutions.
For one.
Yeah. I know I don't know, but I'm assuming you did. Yeah. Okay, yeah. Mhm.
Instead of erasing our, redo our work and, you know, anyways.
Yeah.
That was our issue, is you're driving accidentally running breakfast, you guys are struggling.
Uh-huh. Yeah, it's like a real short one. Now, the way we can start analyzing this is let's use Kirchhoff to start analyzing this. So what I'm going to do is I'm going to go clockwise around this circuit. Okay, so what am I going to get? I'm going to get delta V of the battery, delta V of the resistor, delta V of the capacitor equals 0. Now, if I go clockwise, so what's the sign on the electromotive force going to be? I'm going from negative to positive across the battery. So that'll be positive. Okay, what about the delta V across the resistor? You see, I didn't give you current. You have to know by now which way current's going. What? Yeah, which way's current going? That doesn't tell me anything. That way. What about that way? No, what about that way? What about it goes that way at one point? It goes that way at one point. Which way does it go? Like clockwise or counterclockwise? Okay, current goes clockwise around the circuit. So at one point it goes that way, at one point it goes that way, at one point it goes that way, at one point it goes that way. Yeah, clockwise. So telling me, yeah, it doesn't tell me anything. That's only one branch of the circuit. No. You taking your hand and going, yeah. No, doesn't tell me anything. So it goes, the current goes clockwise. So go across the resistor. So you're going clockwise, the same direction as the current, go across the resistor. Negative. So that's going to give you negative IR. What about the capacitor? So you could say, Remember the poles of your capacitor are gonna line up with the battery? The side of the battery they're connected to? And if I'm going across the capacitor, positive to negative, what do I get as the sign on my delta V? Negative. But what is delta V for a capacitor? Nope. What's the equation for delta V of a capacitor? Find it. Uh-huh. The first 5 questions on the exam, the book will help too, so. It is. Okay. Now. So what we can say now. And. Oh, let's see here. And then, so, okay, let's see, how do I want to do this? Okay, so now we need to say, what is the definition for a current? What is the definition for current? Nope, think of it in terms of a rate. Nope. Huh? It was like the very first equation from this chapter. Uh-huh. Yeah, so your rates are going to be over delta T, huh? Delta Q, there you go. So we're going to have R. Okay, so we need to end up getting some kind of equation in terms of time, where Q is defined by terms of time. How do you think we're going to do that? We are going to solve a. Sonia's smiling. She knows what we're going to do. Huh? I think this is the exam y'all are going to start doing calculus. But. Okay, so we are going to have to solve a differential equation. Well, there's the door. Just giving you a warning. Now, the first thing I want to do is I want to combine the right side of this equation. Tell me how I got here. How'd I get there?
Multiply times C over C.
Uh-huh, yeah.
Multiply times E1.
Yep, so I multiply the electromotive force by C over C, then they both have a denominator of C, and so I get there. Now, what I'm going to want to do now is, okay, so I'm going to have on this side, because I need to get the Q on the side of the DQ, and I need to get the RC and the DT over by themselves. I'm going to start using primes. You'll see why. And that's the equation that I'm going to integrate. Go 0 to Q. Yeah, let's go ahead and pull the 1 over RC out front. Now, just looking at this, what's your gut feeling that the solution might be? We've done a number of these. You don't have a gut feeling yet on what the solution to this might be? What does it kind of look like? Yeah, like for example, what if I got rid of the capacitance times the electromotive force? Oh, it does, doesn't it? It is going to come out as a natural log. However, this is the first time you guys have ever seen this. We have to do a fun little thing called U substitution.
My gosh, high school calculus. Oh my God. I have strongly jumps out. My sister don't do that. No. No. And yet, the one
So that means that EU is going to equal, or okay, so that means now this will be a negative now, so du, and then again, this we can leave the way it is, RC. The right side's easy to do. So you see your gut instinct is correct. We end up with a natural log. Okay, so then let's substitute the U back in and evaluate from 0 to Q. Now that's kind of a shortcut way to do it. Most of your math teachers would tell you to change the limits of integration, but I don't like to do that, so. Okay, so what are we going to have? We're going to have minus. I should make that a square bracket. I don't know, we're doing it today, you should know it.
This is an example.
No, not yet.
Oh, this isn't an exercise. Same like the exercises on there, which is an example.
Yeah, you guys are so lucky that I actually can't make you do calculus on an exam. Oh, I would. Oh, oh man, I wish I could. Boy, do I wish I could. If you just accept it, it makes things easier. If you stop resisting it,
I'm trying. Oh my God.
who broke your brains?
This bio.
Like you are broken right now. I don't. Okay, so now we can say we can combine the natural logs. And what happens if I now make that natural log negative? Yeah, it just flips the inside. All right. So that's going to give us
They're like giving 3 dots, and I'm like, yeah.
3 dots. What do you mean 3 dots?
Like the therefore. Everybody's.
That's a logic symbol. That's not difficult.
Yes, it is.
So you mean,
Like that, you gotta prove your math.
yeah, that's called syllogistic argumentation. Oh, there's a whole alphabet of logic statements.
Better, I gotta like that, the better side of the beat algebra, but when they start putting dots in that, I'm like, yeah.
Yeah. Now, let's get rid of the natural log. How do I get rid of the natural log?
E.
An E, there you go. See, you guys are learning. No, not everyone knows that. Well, you will actually, but
One letter?
all righty. So then negative Q. And so then if I factor that out, what goes inside the parentheses?
1 minus 1.
Okay. Now,
Is that like RC cars?
yeah.
Wow. All right.
So once the capacitor has been fully charged, you're going to have so once the capacitor is fully charged, your current, you're going to have a charge on there of C delta V. So what is that going to be? So C delta V, which our delta V in this case is what? So you can either call it Q max or Q final. That's going to be, so Q max is after the current completely shuts off because the capacitor is fully charged. This is usually why you have circuits with multiple switches in them. Because you'll turn a switch, you'll flip one switch, it charges a capacitor. Then that switch opens, and then when you need to use the energy in that capacitor, another switch closes, which creates another loop in the circuit. So, for example, this is why you could tell that a lot of the windmills were nothing but political stunts, because people hooked the windmills straight into the people hooked the windmills straight into the grid, when what you should have done was hook the windmills to capacitor banks. And so as they're running, you have one or two, like a couple capacitors that are being used, others that are being charged. That way you have a constant flow of electricity. Now, they hook them straight into the grid, so when the windmills stop running, electricity stops flowing. And that's how you know it was a political stunt instead of actual engineering. If there were engineers who designed it that way, they're stupid. So now, having them hooked directly to the grid is not a good idea. You want capacitor banks. That's going to be a separate thing. Now they might be in the panel, but you're going to have the solar part that actually collects the sunlight, and then electricity will be transferred to capacitor banks. You just close, like, if you look at like the most simple circuit where you have multiple switches, the one switch closes, the other opens while the capacitors are charging. Then that switch opens, cuts off the charging circuit. The other switch will close, which is the circuit for the use of the stored energy. So it'd be like well, you could, but it'd be pointless. I mean, you'd be draining the capacitor as you're charging it. It wouldn't. What you usually find on those houses, if you look, you'll find, and you could do this with car batteries. So you will find a box somewhere with like multiple batteries in it, and the panels are charging some of the batteries while others are being used. And it just kind of round robins the batteries. As they get full, then they open up and supply. Mm-hmm. Yeah, but that's a different energy source. Yeah. So you say, like, you have to think about the output of the energy source you're using, what it does, how it works. And you have to design the system appropriately for the energy source. So to the solar powered what? You just have to create a separate circuit. So the current of a system also is going to change over time. Remember that graph, how the current decreases as the capacitor charges? So if we go back, If we go back to our original Kirchhoff equation, because that tau is actually going to be something called the timing constant. So that timing constant can give you an idea of like, well, after a certain amount of time, this is how much of the circuit, this is how much of the capacitor is charged. Like, for example, when your timing constant, your R times C equals like your little t, your time, when those two are equal to each other, you have about 63% of the capacitor charged. So you can actually get an idea of how fast the capacitor is going to charge. Well, yeah, because remember, it's an exponential curve. So you're going to get so much of it, then you're going to reach another timing constant, you'll get more, and so on and so forth. But it's going to be a measure of the charging in the capacitor. Mm-hmm. Now, in this case, it's the timing constant. We will get there because we'll have to do it with magnetics. Well, as I said, we could start doing quantum mechanics and get into the Hebrew letters. There is a universal constant called the Aleph factor. So then we say our I as a function of t and so this epsilon 0 over r, that is the initial current of the system. Because it's a function of time. So, like, for example, we talked about, again, you can look at the timing. So in this case, when your timing constant equals t, your current has decreased to about 37% of the original current. So again, these are going to be factors for timing the charging of your circuit. Where yeah. Mm-hmm. What?
Yeah.
It's when the time that you're charging the circuit, it's not torque. The timing constant. It's torque. R times C is R times C is the circuit. And then when your time T actually equals your R times C, that's when you have a point where C equals the timing constant. And so you'll either have like 37% of your original current left, or about 63% of your capacitor will start. Of course, yeah. Well, this installs the model,
I just write every single example problem and every single problem on my.
If that makes you comfortable.
Yeah, something I'm not. I'm full and that's the basic. Like, if you don't give a max. What is that lower? What is it?